Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on computer communications and networks. We're still in the network layer chapter, and in the previous lecture, we talked about the IP address, the structure of the IP address, the idea that the IP address has a network ID and a host ID, or a network number and a host number, and we talked also about the concept of subnetting and the use of the subnet mask. However, in our discussion, we assumed that IP addresses belong to specific classes. So we have three main classes of IP addresses: class A, class B, and class C. The difference between these classes was in the number of bits assigned or allocated for the network ID versus the host ID. So in class B, for instance, the host ID has 16 bits, which means that our class B network can accommodate 2 to the power of 16 hosts, to be more specific, minus 2, to avoid the all zeros and all ones. And the class C network has only 8 bits as the host ID, so it can accommodate up to 256 hosts, to be more precise, again minus 2, so only 254 hosts. Now the problem with the classes is that sometimes class C would be too small, so it cannot have more than 254 hosts. However, class B is way too large because it can accommodate up to 2 to the power of 16 hosts, so more than 65,000 hosts. So what is the solution to this? Of course, we talked about some solutions. We talked already about one possible solutions to be more efficient in allocating IP address space and to avoid wasting IP addresses. We talked about the idea of subnetting. So within the classes, so within the use of the classes, class A, B, or C, we can do subnetting. So a network can be divided internally into subnets so that we don't have to go and use an additional network ID. This is already a good idea. It saves IP address space. However, we can do something else as well by forgetting about the classes completely. And this is the topic of this lecture. It's called classless addressing. So IP addresses that don't belong to a particular class, and that's how networks work nowadays, right? We can also call it classless interdomain routing, CIDR or Cider. That's how it's pronounced. It can be thought of supernetting, and I will tell you why. Now, the idea is that we can get rid of the address classes. So we will not talk about class A, class B, and class C anymore, as we will see in our details and as we will see in our beautiful example that we will end this video with. Now, imagine the following. I have a network for my organization. And I need to allocate IP addresses. I need to assign IP addresses to the machines connected to my network. So I have to choose a class. Assuming that we have the classes, I have to choose a class. So I think class C is too small because it cannot have more than 254 hosts. However, class B is too large. It can have up to 65,000 and more hosts. Now, as a solution to this, I might think as follows. I might think, let me use a block of IP addresses. Let me use a block of IP addresses that corresponds to several class C network addresses put next to each other. So basically concatenated next to each other. Every class C network, by the way, every class C network can have 2 to the power of 8, so 256. Of course, the first one is the network address and the last one is the broadcast address. So the actual addresses for the actual host is 254, but in total we have 256 addresses, which is not enough. If I use several of these class C network IDs, I can be using a total of more than 256, so multiples of those. However, still less than 65,000, which might be more efficient. So this is basically the first way that we will look into this, and then later on, as we will proceed, you will notice that we will actually forget about the classes altogether, and we can be more efficient by defining, if you will, we can define any class that we want. Now, let me give you a small motivating example here. So we have an organization that will have 256 hosts, exactly 256 hosts. Now, these are too many for class C, because for class C, we cannot have more than 254 hosts. You know, the all zeros and all ones as a host ID, right, is reserved. One of them is used as the address of the whole network, of the whole subnet, and the other one is used as the broadcast address. So class C will not work. with 256 actual hosts. But Class B can give us more than 65,000 and something hosts. So what is, if I use Class B, which gives me a total of 65,000 addressees, the Class B network ID will give me a total of 65,000 IP addressees and even more, 65,500 and something, right? Now I'm using only 256 of them. So let's divide to get the efficiency, the utilization of the available address space. 256 divided by 65,000 is about 0.39%, 0.39%, which means in this case, if I'm having only 256 hosts and I use Class B because Class C is too small, I will end up utilizing less than 0.5%, not even 0.5% of my available IP addresses, which is a huge waste. Now, the solution here to this problem is, instead of using a Class B network, instead of using a Class B IP address class, we can use several contiguous Class C networks. Each Class C network ID will allow for 2 to the power of 8 addressees, 2 to the power of 8 hosts. Let me use several of those, which will give me a block of IP addresses. It will give me a block of IP addresses, which is significantly smaller than 65,000, which will enhance the efficiency. It might still be a little bit unclear. So let's look at an example with numbers. Let's say for our organization, we will assign several Class C network numbers. Instead of using only one Class B network ID, we will use several Class C network IDs from 192.4.16, just an example, from 192.4.4.16 until 192.4.31. By the way, if you review the Class C IP address structure, it begins with 110. It begins with 110 in binary, and if you convert 192 into binary, you will basically verify that it begins with 110. So what you see here is, in fact, a Class C address. In addition to this, so we have the 3 fixed bits. For the Class C IP address, we have the 3 fixed bits, 110, followed by 21 bits that represent the network ID, and then followed by only 8 bits that represent the host ID. So the fixed bits for a Class C network are 24 in total, the 3 fixed ones and the 21 network ID, so 21 plus 3 is 24. We have 24 fixed bits, and then the variable bits for the different hosts are only 8. So what you see here are network IDs, 24 bits. Network IDs that include the 3 fixed bits, but these are fixed anyway. 192 is a decimal equivalent to 8 bits. These are another 8 bits, and then these are the third 8 bits, so 8 plus 8 plus 8 plus 8 is 24. 8 plus 8 plus 8 is 24, and we have 24 fixed bits in total. So what you see here, 192.4.16, or its binary equivalent, represents the network ID of one of the Class C networks that we will be using as IP addresses. And then the last one is 192.4.31. So we will use 192.4.16 and .17 and .18 until .31. So these are 16 Class C network IDs, 16 different Class C network IDs. If I'm using those instead of a single Class B address, of course, the single Class B network ID, if I'm using only one Class B network ID, I will have 16 bits for the host ID, which will allow for 65,534, 2 to the power of 16 in total, but the actual host IP addresses will be 2 to the power of 16 minus 2. Now, if I'm using instead 16 different Class C addresses, what is the block? Let's look at this. What is the block of IP addresses that I can use for my organization's network in this case? So what is the first host IP address on that network here, on that Class C network? Of course, 192.4.16 is the network ID, because these are the fixed bits. Again, in Class C, we have 24 fixed bits, the 3 that are fixed plus 21 representing the network ID, as long as we're using the classes, and we have 8 bits at the end that represent the host. So the first possible combination for the 8 bits is just 8 zeros. So in decimal, it would be 0. So for this network here, for this Class C network, the first IP address available is 192.4.16.0. So this is the first IP address available here. And the second IP address available, obviously, on this network is 192.4.16.1 in binary 0, 0, 0, 0, 0, 0, 7 zeros and 1, right? What is the end of my IP address range here? What is the last address in my block of IP addresses? Obviously, it's on the last network, and more precisely, it's the last address on the last network. So 192.4.31 is the network ID of the last network, the last Class C network address that we're using, and then dot 256, which corresponds to a binary sequence of 8 ones. So we start from the first network. So our first address, again, the IP address range that we will be using for our organization's network starts with that IP address range, starts with the first address on the first network, and ends with the last address on the last network. So since we have Class C, again, I'm repeating myself, since we have Class C, what you see here is a network ID. To get an actual IP address, we add the host ID, and since we want the first one, it is .0, 8 zeros in binary or a decimal 0. And since we want the last address on the last network, so the network ID again is 192.4.31.8 binary ones in decimal equivalent to 256. So this is my IP address range. That IP address range is not the same as a Class B network, because in the Class B network we have 65,000 addresses, and it is not the same as a Class C network, because in the Class C network we have only 256 addresses. This is something in between. Let's have a deeper look here. 192.4 is fixed in the first and in the last, and obviously in everything in between. So 192.4 is fixed. What I want to do here is to convert these addresses into binary so that I have a deeper look into my range of IP addresses. However, since 192.4 is fixed anyway, so let's keep them in decimal. 192.4, let's keep them in decimal here. They have a binary equivalent, of course, but this is the same as that, so it will not change. And then this is 16, and this is 31, so this digit is changing, 16, 17, 18, 19, until 31. So let's convert it into binary. 16 in binary, 8 bits binary is 0, 0, 0, 1, 0, 0, 0, 0. This 1 followed by 4 zeros is 16, and to complete the 8 bits, we have to put 3 zeros to the left here. So this binary sequence, the third octet here, 0, 0, 0, 1, 0, 0, 0, 0, this is the equivalent of the decimal 16. And then the last range, the last address here is 192.4, because this is fixed. And then 31 is 0, 0, 0, 1, 1, 1, 1, 1. So that's the 31 here. 3 zeros followed by 1, 1, 1, 1, 1. 31 is 5 ones, right? Preceded by 3 zeros, so that we have 8 bits in total. Of course, we have to convert also the last digit, which represents the host ID. And in the first address, it is just 8 zeros. And in the last address, since it's 256, so it's represented by 8 ones. Again, I have just converted in this bullet here, in the second bullet, I have just converted the range of IP addresses that I can use for my network into binary. But I just skipped converting the first 2 digits into binary because they are the same anyway. They will never change. In the whole range, I have always 192.4, because this is in the first and in the last, so obviously it's everywhere in between as well. So 192.4, the first 16 bits. And then I go to the 16, I convert it into binary, which is 0001, followed by 4 zeros, and then the 0 into binary is 8 zeros. So this is my first IP address in the range that is assigned to me, right? The last IP address in the range that is assigned to me, 192.4, I also left it in decimal, right? Or equivalently, it has a binary equivalent, which will not be different from this one. And then the 31 is 0001, followed by 4 ones. That's the 31, and then followed by the 256, which is 8 ones. So my IP address range is from this value until this value. Let's have a look here. How many fixed bits do we have in that range? How many fixed bits in the first address in the range and the last address in the range? And then obviously in all addresses in that range between this address and that address. How many fixed bits do we have? 192 is fixed as a decimal, and 4 is fixed as a decimal, obviously, so these are 16 bits. In addition to this, we notice that 0001 is also fixed. It does not change. It is only the last 12 bits that are changing here, So we can say that this address range, and equivalently, let's get used to saying a block of IP addresses. That block of IP addresses from the first address until the last address has 20 fixed bits. Since we have 20 fixed bits, obviously we have 12 variable bits representing the host. So what does this range of IP addresses, or that block of IP addresses, look like? So that block of IP addresses is neither a Class C network anymore, because in a Class C network, we have only 8 bits representing the host. So the variable bits are always representing the host. All machines connected to the network will share the same network ID, right? So those fixed bits are supposed to be equivalent to the network ID, and they have to have, these machines on our network must have different host IDs. Since these are the variable bits here that will change from host to host, it means that these bits basically will represent the host ID, right? So in this range or block of IP addresses, we have 12 fixed bits, and we can think of them as the network ID, right? And we have 20 fixed bits, and we can think of them as the network ID. We have also 12 variable bits from address to address. They start from 12 zeros until 12 ones, and then in the range we have everything in between. So we have 12 variable bits that represent the host address. If this is a range of IP addresses that gets allocated to my organization, now I can start using this range to give people or machines IP addresses once they get connected to the network. But as a rule, the first IP address in the range is always used as the network address. So this is the address that represents the whole network. This is the address that reflects or represents the whole network. And the last IP address in the range is always used as the broadcast address in my network. So if I want to send a broadcast message to all machines connected to my network, I will use this last address as the broadcast address. Now, addresses in the middle, these are the actual addresses that we can allocate to the actual machines or hosts in our network. So the fixed bits represent a network address, right? Sorry, the first address in the range represents a network address, and the last address in the range represents the broadcast address. Now, these fixed bits, how do we call them? What do we call them? So to have some new names here as well, just to indicate that we're talking classless, right? The fixed bits are called the prefix, and the variable bits at the end are called the suffix, right? But we know the prefix bits reflect the network, so they represent the network ID or the network number, and then the suffix bits represent a host ID or a host number. Here in this example, according to this IP address range, we noticed that we have 20 fixed bits, so the prefix length is 20, right? The prefix length is 20. Let me mention something here. So what does this represent here? Let's compare that. We have 20 prefix bits. We have 20 fixed bits that represent the network ID. How does this compare? Let me go back to the IP address classes. How does this compare against the different classes that we had originally? Class A, Class B, and Class C. Class C has 8 host bits. Class B has 16 host bits. Class A has 24 host bits. In our range that we dealt with in the example that we're talking about in the classless IP addressing topic, we noticed that the host bits are 12. So it's more than Class C and less than Class B. So if I'm using this range of IP addresses, as if I have created a new class, something like B dash, so it's not a B and not a C. And that new class of IP addresses is using 20 bits as the network ID and 12 bits as the host ID, and this can be done arbitrarily. So depending on how many hosts I need. I just need to choose how many host bits I need actually to use, and then the rest will be network bits, and this can be done in any way I need, basically in a continuous way, so we can forget about the IP addresses completely. Just a couple of facts before we continue. Even when we use classless IP addresses, even if we use classless IP addresses, we know that the first address represents the network address. However, to be clear, if I'm just mentioning the first address, of course here the number of fixed bits was clear because I have the first address and the last address. I'm mentioning the first address and the last address, and by looking into them, by comparing them, I count how many fixed bits I have. But to be efficient, let's just mention the first address in addition to the number of fixed bits. So that is the network address. So the network address, the IP address that represents this network here, my organization's network, is 192.4.16, 192.4.16.0. This is obviously the first address in the range, 192.4.16.0, and we agreed that this is the network address. But since we are mentioning just this network address alone without mentioning the last address, so it is very useful that we put a slash here and then we mention how many fixed bits do we have. So the way we express the network address in classless addressing, and we also call it the Cider notation. So the way to express a network address or a network IP address using Cider notation or using the classless IP address notation, we mentioned the first IP address in the range, which is the network address 192.4.16.0, 192.4.16.0 in our example, and we say /20, which is the length of the prefix length. So once you see that, let me go backwards. Imagine that this is the only thing that you see. If we say our network is using a block of addresses which has a network address 192.4.16.0/20. What does this mean exactly? It means that the IP address range that I can use for my network starts with this address. It starts with this address and it has 20 fixed bits, which implies, of course, 32 minus 20 is 12. So this implies that we have 12 variable bits. Once I know which are the variable bits, of course, I can create the whole range of the IP addresses. If this is the first address, if I convert this into binary, of course, and this is the first address, and I know that I have 12 variable bits representing the host, I can just change those throughout the range. Obviously, it will end with 1111 with 12 ones, and then I get the last IP address in the range, the IP addresses that I can use for my actual machines. So better stated, the actual IP addresses that I can use for the actual machines connected to my network will be everything in between these two addresses, right? Now, in the classless addressing, scenario, we also have a subnet mask, right? And the subnet mask will reflect how many fixed bits we have. Remember, the subnet mask was a sequence of ones followed by a sequence of zeros. We have ones in the bit positions that reflect the network and subnet ID if we have a subnet, so network ID in general. And we have zeros in the bit positions that represent the host ID. So for our IP address range, or for our block of IP addresses, what is the subnet mask? Since we have 20 fixed bits and 12 variable bits, it's very easy. The subnet mask will have 21s followed by 12 zeros. 21s followed by 12 zeros. 21s, 8 and 8 is 16, right? 255 is 8 ones. 255 is 8 ones, so these are 16. And then I have another 4 ones to finish the 20. So which means the third octet will be 4 ones and 4 zeros. 4 ones and 4 zeros is 240 in decimal, and then I have the remaining 8 zeros, which is the decimal zero. So the subnet mask that represents my network, my block of IP addresses, is 255.255.240.0, which is a subnet mask that consists of 20 ones at the beginning followed by 12 zeros. The bitwise logical AND between an IP address and the subnet mask still has the same idea. So if I imagine this is my IP address range. If I take any address in the range, any address between 192.4.16.0 until 192.4.31.256. Let's take any address in the middle. Let's imagine it is, as an example, 192.4.16.128. It's an arbitrary address in my range. I can use any other one in my range, including the first and the last one, right? If I take this IP address, which is a valid IP address in my network, and I do a bitwise, bit by bit logical and with the subnet mask. Remember, the subnet mask has 20 ones, the subnet mask has 20 ones and 12 zeros. So if we take this IP address and do a logical AND with 12 ones followed by, with 20 ones followed by 12 zeros, the result of this bit by bit logical AND operation will be as follows. The first 20 bits of this address will be preserved as they are, but the last 12 bits will be replaced by zeros. Of course, we can do that in binary very easy and then convert into decimal, and you will find that the answer is 192.4.16.0. It's not surprising. What is 192.4.16.0? It is the first address in the range, which has 12 zeros. And this is what we use as the network ID. Remember, in our previous discussion, when we dealt with class-full addresses, addresses that belong to the classes, if we take a subnet mask and then we do a logical AND with an if we take an IP address and then we do a logical AND with the subnet mask, what we're doing is that we're masking the host, we're replacing the host with zeros, and we maintain the network and subnet ID, right? Which means we are getting the address of the network that we belong to, that this host belongs to. And in the classless addressing scenario, we are doing pretty much the same thing. So this was our description of classless addressing. Let me just mention this as a general scenario here, as a general illustration of this idea. We know that any IP address is 32 bits. Any IP address is 32 bits. And we know from before that the IP address is supposed to have a network number and a host number to basically stray away from classes, to basically avoid using the restrictions of having only the three classes A, B, and C. According to classless addressing, what we can do is the following. We can choose the network ID to have any length. We can choose the network ID to have any length. Let's say we use L bits in general as the network ID, and this is what we call the prefix. So the prefix are the first bits, the first number of bits in our IP address that are fixed because they represent the network ID. Let's say it is L bits, which implies that the host number will have a number of bits here. The number of bits representing the host will be 32 minus L. In total, the IP address is 32 bits. The prefix is L, and which implies that the suffix representing the host has a length of 32 minus L, and that L can be chosen arbitrarily, which means that we have the continuous counterpart of using the classes. You can think of the class-full addresses as a discrete scenario. We have only class A or B or C, but we have nothing in between. But here, since we can choose the prefix length as long as we want, and the suffix length will just be 32 minus L consequently, and that L can be anything. So we can slide this back and forth, which means that we can create any class of IP addresses according to our needs. We can basically assign to our network any range or any block of IP addresses, forgetting about the classes completely. I hope this is clear. If it's not 100% clear, once we talk about this example, it will become 100% clear. So now let's look at a numeric example. So this is our numeric example, and the purpose of this example is to illustrate basically the use of classless IP addressing. So you will see that the first address in the block of addresses, so if we have a block of addresses assigned to a network or to an organization's network, the first address in this block or in this range is the network address, and the last address in this block is basically the broadcast address, and then addresses in between can be assigned to actual hosts, right? We will see the use of subnet masks, and most importantly, we will also see that even with classless addressing, we can still divide our network internally into subnets. So similar to the case of class-full addressing, in which we use a class A or B or C network ID, and we were able to internally divide our network into subnets. that same idea can be done with classless addressing as well. And I thought the best way to explain, to illustrate this idea of subnetting is through the example right away. So in our example, we have the following. An organization has been assigned the prefix 212.1.1.0/24. So what does that mean? This is the IP address of the network. This is the IP address of the network of our organization. And what you see here, since we say the IP address of the network is always the first address in our block of IP addresses that is assigned to us. So what you see, 2012.1.1.0 is the first address in the block of IP addresses allocated or assigned to our organization, slash the length of the prefix, slash the length of the prefix. So what we say here is that this is the first IP address allocated or assigned to us, and among those bits, among those 32 bits, 24 bits are fixed. 24 bits are fixed, representing the network ID, and the rest of the bits, which is 8 obviously here, 32 minus 24 is 8, the rest of the bits are representing the host ID. So 212.1.1, these are 24 bits, 8 and 8 and 8. 212.1.1, this represents the network ID according to this notation here, and that 0.0 at the end, which corresponds to 8 binary bits, right? That's the host ID. Now, an organization has been assigned the prefix 212.1.1.0/24. Again, this is the first address in the range assigned to us, and the number of fixed bits is 24, which means that the number of variable bits representing the host are only 8. However, we want to divide our range of IP addresses. We want to divide our range of IP addresses into 4 subnets. We want to form subnets for 4 departments. Department A, B, C, and D. Each one of the departments, we have the number of hosts that we need. So Department A will require 75 hosts. Department B requires 35 hosts. Department C requires 20 hosts. And Department D requires 18 hosts. So this is basically the problem that we have. We have a range of IP addresses in a classless way assigned to an organization, and that range of IP addresses, that block of IP addresses, needs to be divided into 4 subnets, one for subnet A, B, C, and D respectively, and for each one of these subnets we are given how many hosts we need. So what is required? 2 questions. For each one of these subnets, give the possible arrangements of subnet masks to make this possible. So what are the subnet masks used so that we implement this subnetting? You will see that for each one of the subnets, we have a subnet mask so that we basically implement this particular subnetting, A, B, C, D, with 75, 35, 20, and 18 hosts respectively. And for each one of the subnets, A, B, C, and D respectively, for each one of these subnets, we need to specify the first address in the range and the last address in the range. So for subnet A, what is the first address that can be used by this subnet, and what is the last address that can be used by the subnet, and the same for the other subnets as well. So let me look at the solution here so that you learn what we should be doing step by step. So the given information here. So let's start with this. An organization is using the prefix 212.1.1.0/24, which represents again, over and over again, this is the first address in the range for this organization. So 212.1.1, and then the 0 is 8 zeros, right? Why did I use the last digit here, the last octet, to convert into binary? Since we have /24, /24 means that among those bits here, among those bits, 24 are fixed, representing the prefix. 24 bits means 8 plus 8 plus 8, so the 212 and the 1 are fixed anyway. So for efficiency, we have chosen not to convert them into binary because these numbers will stay everywhere, right? So 212.1.1, this is the network ID, the 24 bits, the prefix, because the prefix length is given to be 24, which implies that the suffix representing the host ID is 8 bits, so that we can enumerate the full range of IP addresses. It is very useful that we convert it into binary. So what we have done, if you want to go in a systematic way, we convert this into binary. We convert the IP address into binary, and then we observe what are the host bits. They're just 8. 32 minus 24 is 8, and we enumerate them all so that we work out the range of IP addresses. So when we say an organization is assigned the prefix 212.1.1.0/24, it's equivalent to saying that this organization is assigned or allocated a block of IP addresses starting from this address and ending with this address. Why starting with this address? Because it's the same as this address. The network address is always the same as the first address. Why ending with this address? Because /24 means 24 network bits, or the prefix, which implies 8 host bits, or the suffix. So these 8 bits, the last 8 bits are the bits that will be changing. And if we go through all possible combinations from 8 zeros, 7 zeros, and 1, 6 zeros, 1, 1, 6 zeros, 1, 0, followed by 6 zeros, 1, 1, and then all other combinations, it will end with 8 ones, right? So from all zeros until 8 ones. From 8 zeros until 8 ones. How many addresses do we have here in total? How many addresses? Since the number of host bits are 8, the total number of combinations starting with this one, ending with this one, and everything in between is 2 to the power of 8. Among the 2 to the power of 8, the first one is the network address, and the last one is the broadcast address. So the actual IP addresses that we can assign to hosts in our network are the ones in between. So starting from 1 here, all zeros ending with a 1, and all ones ending with a 0. So these are the addresses. But in total, we have 2 to the power of 8 of them, including the network address and the broadcast address. Now, this is the address range, the full address range that belongs to our organization, right? Now, this range needs to be internally divided into subnets, and this is what we have here. Needs to be internally divided into subnets. And let's start with subnet A. By the way, it is very useful that the number of hosts in each subnet is basically ordered from high to low. This will solve the problem nicely, which is the fact here. So 75, 35, 20, and 18. We have that anyway, so let's consider subnet A. Subnet A requires, this is what we're doing. Please focus with me. Subnet A requires 75 hosts. To cover 75 hosts, how many bits do we need so that we cover 75 hosts? Is 6 bits enough? What is 2 to the power of 6? 2 to the power of 6 is 64, less than 75. Next number of bits that's possible, 7. 2 to the power of 7 is 128. Of course, 128 is more than 75, but 6 bits was not enough, which means that we have to use 7 bits as the host ID. We have to use 7 bits as the host ID for this subnet. It means that that subnet can have up to 128. I know that we need 75, but with 7 bits, we can even increase up to 128. Simply speaking, 6 bits was not enough for 75 hosts. So 7 bits have to be used as a host ID for this subnet, which implies how many bits represent the network? 32 minus 7. This is what we do in classless. How many host bits do we need? And then the rest, 32 minus that number, is the actual prefix length, which means the fixed bits representing the network. So from the number 75 and 2 to the power of a number that we find, so 2 to the power of 7 is 128, which is the smallest number that is a power of 7, that is power of 2, sorry, the smallest number, which is a power of 2, which covers the 75. Of course, the total size of our subnet needs to be a power of 2, because at the end of the day, the host bits, basically we have binary bits, and then the total number of sequences is always 2 to the power of something, right? So 2 to the power of 7 is 128, which implies 7 host bits, and implies as well 32 minus 7, which is 25 network bits. So this is what we know just from the number 75. 7 host bits and 25 network bits. Now, what is the first address that we can use for subnet A? Since we're starting with subnet A, the first address for subnet A is the first address in the network, right? So the first address for subnet A is the same as the first address in the network, 212.1.1.0 in decimal. Here, 1.1.0 in decimal, but we're expanding the last 0 in binary because we have 8 host bits in total for the whole network, right? So we're expanding 212.1.1 in decimal, and then the rest is in binary, .0.000000008 bits. Why did I encircle 7 of them? Why did I encircle 7 of them? Because for subnet A, we discovered that we need 7 host bits. So the rest, the other 25, will be network bits. These are 7 that I'm encircling, and those are 25 bits that will be fixed for that subnet. Not for the whole network, but for this subnet. These will be fixed for the subnet. So 212.1.1, these are decimal numbers. This 0 is a binary number. This 0 is a binary number because it belongs to the last 8. Now, since we know that we have 7 bits as the host ID, as the host number, we can simply work out all possible combinations so that we end with the last address. So again, the first address for the first subnet was the first address in the whole network, and we know that we need 7 bits, so these are the bits that we need to expand, so it will end with 7 ones, and these are fixed anyway. So we solved already this question here. What is the first address for subnet A? What is the last address for subnet A? This is the first address, and this is the last address. Of course, these addresses can be converted into decimal, right? These addresses can be converted into decimal, so 212.1.1.0 and ending with 212.1.1. The decimal equivalent of this. What is the decimal equivalent of 7 ones? I believe it is 127. Now, we also need the subnet mask to make this subnetting possible. We need the subnet mask. So what is the subnet mask that corresponds to subnet A? Didn't we know from the beginning that we have 7 host bits and 25 network bits? So the subnet mask, simply speaking, has 25 ones followed by 7 zeros, full stop. It is as easy as that. So the subnet mask has 25 ones. 255 is 8 ones. 255 is another 8 ones. 255 is a third 8 ones. So this is 8 plus 8 plus 8 is 24. So we have one more 1. So we continue in binary here. We have one more 1. So this is in total 25 ones and 7 zeros. If we convert this into decimal, it is 255.255.255.128. Right? Okay. So this is the subnet mask, and we have the first address in our subnet, and we have the last address in our subnet, which solves the question. But in addition to this, for subnet A, what is the network address? What is the address of subnet A itself? The address of subnet A is the same as the first address in the subnet, which is 212.1.1.0 slash the prefix length. What is the prefix length for the subnet itself? It was 25 bits, right? These are the network bits for subnet A, not the 24 in the original one. I'm talking about subnet A. So the network address for subnet A is 212.1.1.0, which is the same as the first address, and then slash 25 because we have 25 fixed bits. Now, this red statement here is very important so that we can continue with subnet B. And this is what I advise you to do. We have obtained already the first address in the range and the last address in the range for subnet A. If this is the last address in the range, what is the next address? The next address, which comes right after it, and this is the one that we can start with for subnet B. If this is the last address, 212.1.1.0.111 and so on, 7 ones preceded by a 0. If we go to the next address, this bit becomes a 1 and these bits become 0. So that's why the next address after subnet A, is 212.1.1 as it is, .1 followed by zeros, which is obviously the first address that we can use for subnet B. Now for subnet B, we do exactly the same thing as what we have done here, knowing that this is the first address. So for subnet B, we need 35 hosts. 35 is 2 to the power of what? 2 to the power of 5 is 32, which is not enough. So the next possibility is 2 to the power of 6 is 64. So we choose 6 host bits. For subnet B, we have to choose 6 host bits, which implies that we need 32 minus 6, which is 26 network bits. Of course, if we use 6 host bits, it means that subnet B could have possibly up to 64 hosts. Actually 62, because the first and the last are not used. However, we need 35 it can support up to 62, but we cannot go with 5 bits, as I've explained here in Subnet A. So in short, we have 6 host bits and 26 network bits. What is the first address in the range? It is that one that comes after the last address for Subnet A. So we are going continuous, right? We're assigning or allocating contiguous blocks of IP addresses to the different subnets. So the first address in the range is 212.1.1.170. However, for Subnet B, how many are the host bits? How many host bits do we need? It's only 6. So let's encircle those 6 bits, which means that the other 26 are fixed. The other 26 are fixed. 8 plus 8 plus 8 is 24. And we continue in binary, another 2 is 26 bits. So the last address in the range for Subnet B will have those as they are because they are fixed anyway. This represents the network ID for Subnet B, right? So the last address in the range will have 6 ones. Instead of 6 zeros, it will have 6 ones. And then the range itself will have all addresses in between that can be allocated to the different hosts that belong to Subnet B. So we have the last address in the range, right? These numbers, of course, can be converted into decimal, right? So that we give the first and the last address in the range in decimal, right? And also, in addition to these things that are required, we can work out the network address. So what is the address itself of Subnet B itself? The network address for Subnet B is the same as the first address in the range. We mentioned that over and over again. The first address in the range, which is 212.1.1.128. This has a value of 128, and then slash the prefix length. What is the prefix length for Subnet B? The length of the, basically the number of fixed bits, which was worked out to be 26. We obtained it ready to be 26 from the beginning, so it is slash 26. That green statement here is the network address. Of course, the subnet mask used, we can also, it was required here in A. What is the subnet mask that we need to implement Subnet B? The subnet mask is basically, simply speaking, 26 ones followed by 6 zeros or its decimal equivalent. 26 ones, 255, 255, 255, that's 24 ones, followed by another 2 ones to make them 26, and then followed by 6 zeros. So if we just convert the last binary sequence into decimal, it's 192. So the subnet mask for Subnet B is 255.255.255.192. Finally, before we go to Subnet C, we have to find what is the next address. It's always a perfect idea. It's a wonderful idea to come up with the next address so that we can start with Subnet C. The next address, so this was the last one. If we go to the next one in binary, of course, 212.1.1 will stay, and the next one in binary will have 1, 1 here, we'll have 1, 1 here, and these bits will flip into 0. So 1, 1 followed by 6 zeros. This is the next address after the last one for Subnet B, and this is precisely the address that we can start with for Subnet C. This is what you see here, 212.1.1.11, 6 zeros. However, we just need to work out how many host bits and how many network bits we need for Subnet C, which comes from the number of hosts that we require. 20 hosts is basically what we require, 20 hosts. So 20 is 2 to the power, what is the closest 2 to the power, which covers 20? Right, 2 to the power 5 is 32, but 2 to the power 4 is 16, which is not enough. So we have to use 5 host bits, which implies 32 minus 5 is 27 network bits, and that's for Subnet C. So the first and the last. First is here, the next address after Subnet B. So this is the first address for Subnet C, 212.1.1.116 in binary, right? But we know that 5 of them are host bits, so let's encircle 5. And these are 27, which are fixed. So to go to the last range, we keep the fixed bits, the last address in the range, we keep the fixed bits, and then we go 0, 0, 0, 0, 5 to the last one in this range, which is 1, 1, 1, 1, 1, 5 ones, from 5 zeros until 5 ones. So again, what you see on top, the first address is the address of the network itself, of Subnet C itself, and the last address is the broadcast address that can be used to broadcast to all machines that belong to Subnet C. And then in between, from 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, and so on. These are the actual IP addresses that can be allocated to the machines that belong to Subnet C. As usual, we need to get the mask. It's a very easy task, 27 ones followed by 5 zeros, or it's binary, it's decimal equivalent actually. So 27 ones has 24 ones already, so 255.255.255, and then we need 3 more to make them 27. So we continue in binary, 1, 1, 1, and then 5 zeros at the end. So we just need to convert this number into decimal, which is 224. So this is the subnet mask, which implements subnet C. What is the network address again for subnet C? The same as the first address, 212.1.1 dot the decimal equivalent of this number 11000000, which is 192, by the way. Check it yourself. So 11 followed by 6 zeros, 11 followed by 6 zeros is equivalent to 192, and then slash the prefix length, slash the prefix length, and for subnet C, the prefix length is 27 because that's the number of network bits. The fixed bits are 27 because the host variable bits, the variable host bits were 5, and this comes from 2 to the power of 5 is equal to 32, which covers the 20. It's the smallest power of 2 number. It is the smallest number, which is a power of 2, covering 20 hosts. So this is the network address. And the next address, we still have one subnet to go, so we need to come up with the next address, which is the one after, right after the last address. So we just need to flip and go to the next one, increment by 1. If we increment by 1, this becomes 111. Obviously, this becomes 111, and then the 5 ones will become 5 zeros. So the next address is 212.1.1.111 followed by 5 zeros, and this will be the first address that can be used for subnet D. However, let's decide on how many host bits do we need and how many network bits do we need for subnet D, and that comes from the number of hosts. Subnet D requested 18 hosts. 18, 2 to the power of 5 is 32. However, 2 to the power of 4 is 16, not enough. So we have to go with a 5, which means 5 host bits, which implies 32 minus 5 is 27 network bits. So when we put the first address the same as that, let's encircle only 5. Just as in subnet C, that's okay. So we encircle 5, these are the host bits, and the other 27 represent the network bits. So this is the first address. To go until the last address, of course, the fixed bits will stay as they are, 212.1.1 decimal, followed by 3 binary ones here, followed by binary 111, and of course, those 5 ones, those 5 zeros will become 5 ones. So this is the first address in the range and the last address in the range or in the block that will be allocated or assigned to subnet D. Of course, the addresses in the middle, again, as I mentioned over and over again, these are the IP addresses that can be assigned to the actual machines, including the hosts that belong to subnet D. Now, let's solve the questions that we need to find, basically, for subnet D. What is the network address for subnet D? The network address is the same as the first slash the prefix size. So 212.1.1.111 zeros, which is 224, which is 224, slash the prefix length, which is 27, because we have 27 network bits, so slash 27. And the mask is simply 27 ones followed by 5 zeros, which is 255.255.255. These are 24 ones, and then followed by another 3 ones and 5 zeros, which has a decimal equivalent of 224. So this is the subnet mask that we use for subnet D. As you notice, the subnet mask for subnet D is the same as the subnet mask for subnet C, simply speaking, because we have the same number of host and network bits in both cases. If we had another subnet E, then of course we have to work out the next address. So if this is the last address in the block for subnet D, the next one is just we need to flip it, which is not possible, obviously. It's not possible in this case because do you notice this address here? This address, which is the last for subnet D, this address is already the last address for my whole network. It's already the last address in my whole network, so I don't have any remaining addresses, and I cannot imagine any other subnet that can be allocated. So this finishes the question. And before we leave you, let me just summarize some rules when you create subnets in classless IP addressing. When you create subnets in classless IP addressing, of course, when we create a subnet, the subnet will receive a block of IP addresses. The subnet will receive a block of IP addresses from the first until the last, but that block is always a contiguous set of IP addresses. So we're not jumping. So each subnet gets a contiguous block of IP addresses. The block size is always a power of 2. So the size of this block is always a power of 2, which is 2 to the power of how many host bits do we have, right? And the first address in the block always has zeros in the suffix, in the host bits, always zeros. And the last address in the block always has ones in the suffix. The first address is used as the network address, and the last address is used as the broadcast address. This is like a summary of some of the most important rules when we create subnets in the classless addressing concept, right? And I hope that you got this, and I hope that you will cover the solution and try to solve it yourself. This will be most beneficial, and see you next time. Assalamu alaikum wa rahmatullah.